So on Friday, what we talked about was finding those integrals with that plus c, those indefinite integrals. That means that this is the general form, right? Like we can find this over any interval. This is the equation. Now, what we are looking at today is what if we have a definite integral? So that means what if we are bound between two strict areas? We did definite integrals when we looked at those areas under the curves. And we also talked about the fundamental theorem of calculus, and what that does is it connects differential and integral calculus. You guys have seen this before, right? Our name for fundamental theorem of calculus is that if f of x is continuous, then g of x is the integral of f of x, and g prime of x can be rewritten as f of x. Now, it is important to have this written down because where the fundamental theorem of calculus comes in, and I'm sure that I know I have talked to my students and your teachers probably talked about it before as well, is that it is normally just used as a proof. So it's like by FTC. Now we're going to turn our attention to kind of like what we're talking about. So we're bringing in together the idea that like, all right, we found the area under the curve. Okay, we found what fundamental theorem of calculus was. Okay, we found the antiderivative equation. Now let's actually substitute some values and make a connection. So if we were not given a picture with shapes that we could find the area of, right? Because we've normally been saying like, oh, here's A, here's B. This area is 12. This area is 15. The total area is 27, right? So that's what we've been doing. And now we're going to say, how do we do this with just an equation? So the second part of the fundamental theorem of calculus states that if a function f is continuous on a closed interval and f of x is an antiderivative, then the integral from a to b of f of x is the same thing as f of b minus f of a. You guys got a little bit of an introduction to this when you guys saw that rule, one of those integral rules with the constant, right? And we'll talk about how that's connected. But the rule that you guys saw on, I think it was Thursday night, question mark, the rule that you saw there was the integral from a to b of a constant. What that equals is that k times b minus a, or k times b minus k times a, which is very similar here. It is important to note, however, and we'll make that connection in a second. It is important to note that while this is lowercase f, this is capital F. So we do need to integrate that function before substituting those values. So when we apply the fundamental theorem of calculus, we do the following notation. So this vertical line comes in, and instead of using the integral, because this is saying that we have already integrated, right? So this line means already integrated. And let's see what that looks like. We want to find the definite integral, or the area under the curve x squared minus 3 from 1 to 2. So we're looking for like the total distance traveled. So first off, let's integrate. And we're going to say that this is the same thing. Add that 1, so x cubed, so 1/3 x cubed, and then minus 3x. We normally, and in the past, we put a plus c. We're going to go over why you don't need that. It's a lovely thing. And we're saying we're evaluating from 2 to 1. What this means, very similar to your Riemann sums in a way, right? It's still sort of a notation, and we're going to substitute a 2, and then we're going to subtract that lower area. And if you think about this from a graphic way, like from a graph, let's just do our graph here. Actually, let's do a little bit better. If I think about this on a graph, right? So let's say here's your curve. And we are going from 1 to 2. It's saying that that distance is all the area to 2. And then we're subtracting out the whole entire area from 1. So we're saying it's this whole thing. So from 0 to 2. So 0 to 2 minus from 0 to 1 and that will give us from 1 to 2, which makes sense, right? We're saying this whole integral minus this piece gives us what we want. So I'm going to substitute this in because I'm saying I'm going from 1 to 2. So I have 1/3 times 2 cubed. So I'm just going to, this is 8/3 minus 6. Let's just leave this plus c in and play devil's advocate for a second, and then we'll show you why it's not needed. Now I'm going to plug in that 1. So this is going to be 1/3 minus 3. Because that plus c is there, I'm not given an initial condition. What you will notice is these c's cancel out. I had students last year, after you distribute that negative, who said that they still like writing the c because it just reminds them to continue writing that c if we have an indefinite integral, right? Like if I'm not given boundaries, if I'm just trying to find that equation, they were like, well, miss, that's fine, but I still like writing the plus c and then canceling it out. If you need to do that, then go for it. But just know that it is not necessary to write the plus c because it is implied that it does cancel out because that same constant, let's say if it were an 8, if you had a plus 8 and then you were subtracting an 8, it'd be 0. Let's say your constant was -2. You get where I'm going. It all cancels out. So then we add these values up and I get -2/3. This makes sense with my graph because in x cubed minus 3, it looks like it's probably going to be mainly below the x-axis. So that area from 1 to 2 is going to be that negative area. Let's look at, I'm going to do a sine, let's do a sine one really fast here. So when I integrate this sine curve, I'm going to get this guy is going to be negative cosine of x plus 1x. I'm going to keep that plus c just because like I like doing that. And we are integrating from 0 to pi. So 0 to pi, you can do a bracket, you can do a line. The reason like I've kind of switched, sometimes I do a bracket so I don't know that, or so I know that that's not a positive one. So like note that like you can use this straight line. I would make sure it's very long so that you don't accidentally use that as an integer. Or you can even say from B to A. It means the exact same thing. So as I'm going here, we're just going to substitute that pi in. So make sure we're continuing with those equal signs because we're continuing this statement. So we're going to have negative cosine of pi plus pi. Remember, we can leave out the c at this point. And then that's going to be minus negative cosine of 0 plus 0. And then I'm going to get, what is this? Cosine of pi is -1, negative 1 is 1. So we have a 1 plus pi. Cosine of 0 is going to be negative, so that is just going to be, oh my goodness, why did I just draw a blank right here? -1, oh my goodness, you guys. So what happens when you make videos. It's strange times. So then when we get this all added together, you're going to get a 2 plus pi. And that is our definite area of this function from the integral from 0 to pi. If you want to do these other two, I would pause the video right now and I will throw the answers up just so you can double check yourselves. All right, here are those answers here. Give it a pause if you wanted to go back over and go through those. Do that math. Remember, rewriting is going to be a key thing here. So multiplying this out, fully expanding part C, I would definitely rewrite 3 square roots of x to 3x to the 1/2. The total change concept is the real world integration. And we talked a little bit about this on Friday. You guys saw this like for a snippet. So if f of t represents the rate at which your 401k changes, just like for derivatives, we always were in forms of a rate, we're going backwards. So if f of t is the rate, the units of f and t are going to be dollars per day. That dt is the number of days, right? And then that ft dt is just going to be dollars, right? Because we're canceling those out. So if I think about this, what that integral from 1 to 31, so this is also talking about the month of January, so that 1 to 31 ft dt represents the total value, or so the value, let's not say total because it's just going to be for the month of January, and we would hope that you'd be doing it for longer, the value of your 401k in dollars for the month of January. So we're looking at that value for the month of January, right? When we integrate that, if f of t is the rate of change, we're working backwards from that rate of change and we're going to that value. Let's look at a few others. If R of t represents the rate at which your pizza changes temperatures in a 470-degree pizza oven 5 minutes after the pizza has been placed in the oven to cook. So we're going from 5 to 20, right? So that is going to be the total change in temperature of the pizza in degrees Fahrenheit from 5 to, we can say t equals 5, to t equals 20 minutes. If you guys want to press pause and try to do part C on your own, that is highly recommended, and then press play and check the answers. All right, here's a good overview. Remember, without that integral, so this a of t minus p of t, we're back to a rate. But as soon as that integral gets thrown on, we are actually looking for the summation of those rates. What we kind of saw on Friday is that we talked about velocity and that connection between velocity and acceleration. So we know that velocity is the rate at which position is changing, right? Because you go from position to velocity to acceleration. So if you have a velocity function and I'm integrating from 5 to 50, what this is your total change in position on the interval, whoops, not 0, 5 to 50 units. And this special name, you may have seen this in physics, is called displacement. So this is your total displacement. Likewise, a of t is the rate at which velocity is changing. So what we are kind of doing now, and you guys have seen this, right? You have your position, so your s of t, whoops, that's usually speed. Let me do an x of t. We're going to do our x of t. We go from x of t to velocity to acceleration, and we've normally just gone this from velocity to acceleration, and now we're going to be working our way backwards. So instead of going to that forward motion, we're now going to say, oh, if I know acceleration, I can find velocity. If I know velocity, I can find position. And if I also know my interval, not only can I find position, I can find the total displacement by knowing position at this time minus position at my starting time gives my total displacement. In class, you guys are going to talk about these special cases for the fundamental theorem of calculus, but before you get to class, you should be clicking on that Khan Academy link in the video description or in your Edpuzzle, and that is part of your homework for tonight, is to finish that Khan Academy before coming to class tomorrow. I'll see you guys then.